In this lecture, we are going to discuss Laplace transform of special functions, one of which is Heaviside unit step function. It is denoted as h of t and is defined as 0 when we are in the interval t is less than 0, and in the interval t greater than or equals to 0, the value of the function is 1. When we draw the graph of such a function, let's see how it looks like. This is t and this is h of t. Now in the interval t is less than 0, which is over here, this is t greater than 0 and this is t is equal to 0. In the interval t less than 0, the definition says the value of the function is 0, so the graph will be on t axis. Leaving a small semicircle at t is equal to 0, because the graph doesn't touches 0, because at t is equal to 0 the value of the function is 1, the graph jumps at 1 till infinity. If we are interested now in Laplace transform of such a function, then we will use definition, which says Laplace transform of f of t is integration 0 to infinity e raised to minus st f of t dt. So therefore, Laplace transform of unit step function h of t is equals to integration 0 to infinity e raised to minus st. Now how about h of t? We are in the interval 0 to infinity, so this side. And in this interval, the value of the function is 1. So therefore, h of t will be 1 when I am in the interval 0 to infinity. So we'll put h of t as 1 into dt. Evaluating the integral, we get e raised to minus st divided by minus s with the limits 0 to infinity. When we put upper limit infinity, we get e raised to minus infinity, which is 0, minus when we put t is equal to 0, we get e raised to 0, which is 1 divided by minus s, which turns out to be Laplace of unit step function h of t is 1 upon s. Taking care that s should not be equals to 0, that is the region of existence. Another way to define unit step function is h of, this is 1, this is 2. What is h of t minus a? H of t minus a is defined as 0 when t is less than a and is equals to 1 when t is greater than or equals to a. And if I say that a is some positive value and trace the graph of such a function now, we'll get let's say a is positive, some value over here. So t is less than a, that means we are in this region and the value of the function is 0. This way. Suddenly at t is equals to a and greater than a, the value of the function is 1. So the graph will be something like this. it goes. So the only difference between h of t and h of t minus a is the function starts over here at 0, and in this case the function starts at t is equals to a. This is called as delayed unit step function. We say this as a unit step because the value unit suggests that the value of the function is 1, and the step suggests that at t is equals to 0 the function jumps from 0 to 1, and in this case at t is equals to a the function jumps from 0 to 1. This is 1. Now if we find Laplace transform of delayed Heaviside unit step function, again we'll use the definition. We say Laplace of f of t, this is integration 0 to infinity e raised to minus st into f of t into dt. So therefore Laplace of h of t minus a, this is going to be integration 0 to. Now I am going to start my integration from here. But what we have observed is in the interval 0 to a, the value of the function is 0, and from a onwards till infinity the value of the function is 1, which says that the integration 0 to infinity should be splitted at t is equals to a. So this will be integration 0 to a e raised to minus st. In this region the value of the function is 0, so this is 0 dt plus integration a to infinity e raised to minus st into, in the interval a to infinity the value of the function is 1, so I'll put 1 over here. So this is 0 plus integration of e raised to minus st is e raised to minus st divided by minus s with the limits a to infinity. This is e raised to minus infinity, which will be 0 minus, when we put lower limit a, we get e raised to minus a s divided by minus s. So this is 1 upon s into e raised to minus a s.